this computer. Ignore that. But so for SN1 and E1, right? So you have SN1/E1. What you're doing is you're taking this is some kind of alkyl group with a leaving group we'll call Y, and you're reacting it with X minus. And depending on which pathway you get a different thing. So SN1 will be like our top pathway here. And in that case, right, you just substitute the X for Y plus Y minus. For E1, you're going to get a double bond in here, right? So that Y-looking thing here is your original alkyl leaving group structure here, right? Plus, is this running out of ink? This is not good. Right, okay, so you can see that. So if you do SN, I put 1s, I meant 2s. I'm sorry. This is not a good start. But replace everything I said with a 1 with a 2. So SN2 and E2. If you were confused, that's why. Basically what you're doing is you're taking something meaningfully reactive, and remember, reactive things are unstable, and you are replacing it with a less reactive anion. Focus on the Y minus here, right? So first off, when you're dealing with SN2 and E2, then you expect to have some kind of big energy difference or stability difference between X minus and Y minus. And they might not be minus. They might be something like an ammonia where it ends up being positively charged when it's bound. But the point is, right, this has one more, the Y here has one more bond than the Y here. So its formal charge goes down by 1 because you're replacing a bond with a lone pair, right? That makes sense to you. And this one, you're replacing a lone pair with a bond, whether it's here to the carbon here or to the hydrogen here. So its formal charge goes up by 1 because now 2 electrons were once in that X's possession, but they are now spread across the bond. So that makes sense to you, right? So the reason that I'm saying this is if you're trying to get SN2, you're going to want to see a big stability difference between X minus and Y minus. And this goes back to the good nucleophile, good base thing. If there's a big difference here between X minus and Y minus, then you would expect that you would get one of these, you could think of more reactive pathways, because it's directly energetically favorable to substitute a Y or an X for a Y. So to put an X where a Y once was. Because of that, the stronger this is as a base, or as a nucleophile generally, the less stable it is with a negative charge, then the more you'll see reactions down this pathway. Basicity and nucleophilicity are basically the same thing. They're both measures of how much X is stabilized by getting rid of that negative charge. But there's some small differences, like, okay, a really big X, like you remember this guy, Kotbu, tert butoxide. I don't even know if you can see that, but there's a whole bunch of CH3 bonds here and CC bonds here that are really unstable, that make it really hard for the nucleophile to directly punch into the carbon that has the Y on it, right? So if we try to do SN2 with this, the nucleophile has to get really close because it has to get to the central carbon, right?
Yeah.
You probably wouldn't even see that much SN2 anyway because I made this a tertiary, but that's not really important. What's important is you can see how it would be it would be more favorable for it to only have to take this H that I drew in here, right? If it just kind of like slides up the bottom instead of going right in the center. That makes sense to you? So because of that, even though this is a stronger base than it is a nucleophile,
Wait,
because
can you repeat? So because it's large, it can't get in there.
Yeah. So for SN2, right? You can imagine this is like the central carbon, and this finger. This finger, because otherwise I'd be flipping you off. You can imagine that this is like a leaving group here, and this is your carbon, right? So if you're doing and this is like a CH3 group. If you're doing SN2, the nucleophile has to get right up into the central carbon. And you can see how there's a whole bunch of, you're hitting both of these, right? Whatever that third group is, that's not good. If you're doing E2, you can content yourself with swinging towards this peripheral CH3 group, right? Knocking
Mhm.
off that hydrogen, making this a double bond. I can't do that biologically. But so now this is a double bond. This hurts. I hope you're learning. But
Yeah, I think I know what you mean. Yes.
yeah, like, so what I'm trying to give you an intuitive sense of is the difference between a base and a nucleophile is really just steric hindrance plays into the nucleophile equation, but not as much into the base equation. And that's why you only see E2 when something is relatively unhindered or relatively hindered sterically, because there's a bigger energy difference for E2, right? You're picking something off the top versus SN2, you have to get right in the middle. If there's a
Mhm.
whole bunch of crowding on that actual alkyl halide or whatever that has the leaving group, the thing that's bound to Y, then it's going to be a lot harder to get in. And that's why primary alkyl halides are so much better at SN2 than secondary tertiary. That's why secondary is so much better than tertiary, right?
Mhm.
Make intuitive sense?
Yes. So is there
So
anything else other than um, size that would go off the trend of like nucleophiles and basicity being the same?
yeah, it's first you have to remember it's like the combination of the size of the base or the size of the negatively charged X minus and the size of the thing that's bound to Y. So in our cases, it's usually going to be an alkoxide plus an alkyl halide, right? So both of those. This guy right here is this cotbu tert-butoxide is so sterically hindered that even with a primary, um, even with like a primary alkyl halide, there's so much junk right here that it's probably not going to function as a nucleophile. Now, I don't love explaining things that way because we only know that because we've done experiments, right? Like, so instead of memorizing primary terbutoxide doesn't work, like, get the idea of if there's like a certain threshold that I don't want you to quantify just yet. There's a certain threshold of here's enough space. Let's go ahead with the more sterically problematic SN2.
Mhm.
So that explains why E2 is more favored at higher levels of steric crowding, which is another way of saying, replacing CH bonds with CH3 bonds, things like that. The reason that SN2 is more stable than E2, or more preferred than E2 generally, is that if you look at the products, E2 has a double bond on its alkyl product, right? It's a double bond. And double bonds are less stabilizing than two single bonds. Because, right, when you have two single bonds, you just have the sigma bonds, which go straight. When you have a double bond, you have these pi orbitals that go like this, but have to overlap like this, right? If you remember p orbitals from all the way
Mhm.
back in Gen Chem. So when you have something with a double bond, it's inherently unstable. And that's why we can do so much stuff with double bonds, like you saw in like chapter 5, where you add all that stuff to it, because all those addition reactions have in common is they're taking a double bond system and turning it into a carbon with 4 bonds. So now you've replaced the pi bond with this 4th sigma bond, which is more stable. So what that has to do here is that SN2 is kind of like the default. It's more energetically favorable on its own. This is like a better product, the one with the X and the cross, than this one. But E2 becomes kind of like a necessary compromise when there's too much steric crowding to get to that better situation. Because this is, you know, this whole thing is still more stable than the reactants because X minus is so much less stable than Y minus if you have a successful reaction. So that's why you see SN2 when you do and E2 when you do. I know that doesn't really help because you have a fucking table for your exam, but I still think it's like good to think about things that way. So, are you cool if I go on to SN1 and E1 now? Or
Yes.
all right. So SN1 and E1, and I'm actually going to say SN1 and E1 this time. Life is crazy. So SN1 and E1, you might remember from your table that with these, you're getting no like super good base or super good nucleophile. Another way of saying that is that X minus isn't super unstable. So I'm going to do the same thing as last time, right? Where I have this tert butyl carbon with the Y, which is going to be our leaving group. But instead of an X minus, I'm just going to arbitrarily put like a W because it's not unstable, right? I want to distinguish that between the unstable X and the stable W. And for this, right, you're just gonna run that. You're gonna put it in some kind of solvent, which I'll get to later. And then your end results are, if you do SN1, right? SN1 is going to be very similar to SN2, where you swap W for Y, and you end up with Y minus. This actually should be W minus. Now I think about it, even though. Okay, I'm sorry, I'm going on a tangent. If we do, this marker's going out. This is bad news. Okay. If we do E1, I realize I'm getting close to that glare dot, so I'm going to skip a little bit. If we go to E1, we're going to end up with a very similar product to what we saw with E2, where we have our Y looking double bonded 2-propene plus Y minus plus WH, right? So that should all, hopefully that all clicks by now, like what's going on. So here, though, the reason that you, what separates this from SN2 and E2 is that you don't have a super unstable W here that, by virtue of the stability difference of the anions, can like run the reaction forward, right? So in this case, you have to compromise a lot more. You don't have anything that can like rip this apart like you did last time. So you have to patiently wait until the Y, whatever it is, falls off on its own accord, right? Basically, you'll end up in a situation where this becomes a carbocation, so you just end up having the three methyl groups in a Y pattern, right? That makes sense. And then you end up with Y minus on the end. So that's a common intermediate that both of these have, is this this carbocation plus Y minus. And basically, there are two different things that you can do here. The first is, okay, well, W is not a great nucleophile. It's not super unstable with its negative charge, but this carbocation is super unstable with its positive charge and its octet rule violation, right? So the first solution is just to stuff the W right in there. And because carbocations are so unstable, the steric issues don't become as big of a deal. Basically, right, you're going down a larger energetic hill, going from carbocation to this, than you are going from this to this, which is what you would see in SN2. So, right, that's why you would see SN1. And again, you would expect to see some energy difference between these because once you get this, right, if you're in a solvent that's conducive to forming carbocations, the W could fall off on its own too. So you need the W to be a little bit more stable, a little bit less stable than Y. But like you could also just have more concentration in W.
You mean more stable?
Well, W, basically what I want to be the case is that whenever you end up with this carbocation, there's a larger chance that a W hits it than that a Y hits it. Right? Because if you do that over time, if you think about it, if you have more W's than Y's, which is usually what you do for this, right? So you'll be sticking a solvent on there usually, like a ethanol or something like that. And when you're using something as a solvent, you usually have about 15 or 20 times more of the solvent than the reactant molecules, which means for every Y minus, you'll have like 15 or 20 W's. So then it's just way more likely that whatever happens to come across this carbocation is a W. It helps if the W is a little bit less stable than the Y on its own, but that's not always the case. Like water versus, actually water's more stable than bro. So in this case, I want you to think about it less as a stability issue because it can kind of go both ways, and I realize I misphrased it a little bit. It's more of just an issue of how many W's and Y's there are because the differences in stability between them are probably negligible. for SN1 or E1. The way to get to E1 is that you have W minus take this hydrogen off, or any of these hydrogens, right? It takes this hydrogen off, it gives 2 of its own electrons to take that off, and then that slides the electrons that were in this bond down here, which gives you a complete octet on that carbon, right? So, okay. I wanted to go through that because I think it gives you a better idea what causes there to be a good, like what causes each reaction actually. So for SN2E2, it's driven by the stability difference between the reactant negatively charged thing and the product negatively charged thing, or the product leaving group generally. With SN1 and E1, what's driving it is that there's usually just there's a way to get this carbocation to form, which we'll usually do with some kind of polar solvent that can provide some partial negative charge to stabilize the carbocation once it's formed. So there's a way to get this to form, and then once you get there, it's just more likely that a W hits the carbocation than a Y. So does that make more sense though? Like what makes a good nucleophile, or?
I think so, yes. So basically, unless it's a large nucleophile, unless it's a large base, a good nucleophile is a strong base.
Yeah.
Okay.
Well, a good base is a strong nucleophile. You have stuff like cyanide ion, right? The C triple bond to an N with a lone pair on both atoms. That's a really good nucleophile because it's so slim. So even though it's actually not a strong base, it's so slim that it really doesn't get much in the way of steric crowding. Like there's no annoying carbon-hydrogen or nitrogen-hydrogen bonds to deal with. So as long as it, with a negative charge, is less stable than the leaving group with a negative charge, there's way less activation energy to get that reaction going, which is why Cn minus is a good nucleophile, or NaCN or whatever. But it's almost always true that you'll have strong bases as good nucleophiles. And you might just want to have a table of them or something like that, given the nature of your test. Like, it is a cheat, but basically, yeah. It's a combination of instability with the negative charge plus ability to do the SN2 crowding, get punching your way through the crowd. And you could, if you're really good at punching through the crowd, you don't necessarily have to be a strong base. If you're really bad at it, you could be a strong base and still be a poor nucleophile. But bases are less concerned with that steric hindrance stuff, so you have to, like, base strength is way more important.
Okay.
Make sense?
Yes.
All right.
Sorry. 1 minute.
No.
Sorry, Joey.
Oh. I'm still getting paid for it, regardless of whether you're distracted or not. Don't worry about it.
Okay.
So
is there anything else other than like CN that are common, like exceptions?
Probably not. No, probably not.
Okay.
If you haven't seen anything to that extent in your problems already, I don't think you'd start now. But like, be aware of that. Basically, my goal is to explain this in 20 minutes instead of 3 lectures, which is the way that they do it. It's actually, I think it's easier to understand this way too. But that's goal number 1. Goal number 2 is just so that, like, if you are presented with something totally out of left field and you don't feel like looking at its properties, because you could totally do that now that I think about it, then yeah, in that case, right, it would probably help if you have the ability to derive it. But if you see something that you're unfamiliar with on the test, I'd be surprised. They usually just recycle nucleophiles. So.
Sounds good.
So there's 2 ways we could do the rest of this. 1, I could answer, any questions you have about anything on the test. 2, we can go over your I'm assuming you have a tutorial for this week, right? That's like a review tutorial. So I'm open to whatever. Um, whatever you think will be most helpful for you.
I do have like a list of
Oh,
questions.
that's good. That's
So
good.
if we could do that,
Let's do that. Yeah.
would be great. Okay. They're like on the practice exams.
Hmm.
So I can share my screen with you so you can see like what problem I'm talking about.
Yeah, that would help. I mean, it's not necessary, but it would help because otherwise I have to like go to my computer and find it, and there can
Okay.
be changes between. Yeah, you get it.
Yeah, no, you're good. I have it open so I can
Hmm.
um okay. Well, that doesn't help.
I don't know what you're screen sharing with me, but I don't see anything.
Oh, okay. Oh, sorry. One
Yeah.
minute. Um,
While you're doing that, I'm gonna sit back down in my chair, which is comfy and not making me bend over like that. So,
so this is the one. Yeah. Okay, perfect. Okay, let me know when it shows up on your screen.
okay, I got that you started screen sharing, but I don't actually have anything on my screen right now. Do you want? Oh, there we go. We're good. We're
Okay.
good.
Okay, so for number 3, um, I I got those two, but also why couldn't it be like both of them coming out at you or both of them going back in?
Okay. Yeah, this is an interesting question. So, you're saying why can it be these two but not be CH3 coming out, OH going out, CH3 going in, OH going in?
Like why not all 4?
So basically, you have a CH3 group. So look at the top right carbon on your ring there, right? So you have 4 bonds there, and one of them is to a CH3. And I'm trying to think of how I can explain this. When you have the other one has an open hydrogen, right? So basically, first off, tell me what the stereochemistry of hydroboration is. Do you remember that off the top of your head? You don't have to for your test, which is nice, but
No, but I do have it with me though.
so what it is right, the B and the H, the B and the H in step 1, right, before you get the peroxide and all that, the B and the H are like either both above or both below the molecule. So they're both going to bond to the same side. They're syn.
Okay. Yes.
And you know that the OH or the BH3, which is going to turn into the OH, you know this from just repetition. You know that that's going to be on the less substituted carbon. So you know that your boron thing is going to go down here, and then eventually that's going to be replaced with an oxygen with retention of stereochemistry, right?
I think so.
So what that means, right? So if you know, actually, let me try some really. Oh, I was gonna try to screen share your screen sharing so I could show you my cursor. That was just not gonna work. But
I could stop
well,
screen
don't worry
sharing.
about it. I'll use my words. If you're confused, I'll do it. But I like to think I'm a good teacher, so let's do this. Okay. Right. So you know that you have the B being added to the bottom right carbon and the H being added to the top right carbon, syn. So you accept that. That's what we talked about like 3 weeks ago. That the B and the H are added syn. That's cool with you?
Sure.
Okay.
Are we still talking about just this?
Yeah.
The
Yeah.
first.
I'm getting there. Don't worry.
Okay.
So you know that. You know that the second step for hydroboration replaces the B with an OH but retains the stereochemistry, right?
Mhm.
So if those two things are true, then so if the B and the H that you add are on the same side, remember the H is being added to the more substituted carbon, so that the B can be added to less substituted carbon. So if you agree with that, I'll give you a second to write down. If you agree with that, and if you agree that the OH is unchanged in stereochemistry relative to the original boron, then you have to agree that the hydrogen that you added and the boron, or sorry, the hydrogen that you added and the alcohol group, the OH that you created, are syn. Because the B and H were syn, the B was replaced in a retention of stereochemistry way with the OH. Therefore, the end products, the OH and the H, are still syn.
I see. Okay.
Do you want to try to explain like from here, or do you think do you need me to do it still? Because I want to empower you. I want you to be able to do it.
Yeah, so since the H is syn, technically it's not written, but the H would be dashed also and wedged also on this one. Because it just, yeah, because the OH replaces the B, which would have been in the same.
Yeah. So let's say like take your right side one with the OH coming out. So you would put an H coming out at you on the top carbon, and because the H and the CH3 can't take up the exact same bond, right? The H and the CH3, one of them has to be going in, one of them has to be going out. Therefore, the CH3 and the OH have to be anti.
That makes a lot of sense. Thank you. Okay. That makes a lot of sense.
So that one's just like you have to track everything that's going on in your head, and you have to be a little clever about it. But you can see, like, it's an answer that makes sense.
Yeah. Okay. That helps a lot. Okay. Also, should I? So this question, is it worth my time to try to understand it, or is
Well,
it just?
okay, I could make you understand it really quickly. Are you like in a situation where it's like, where the hell did those products come from?
Yeah.
Okay, so H2SO4. In this case, right, you have two potential acceptors of the H2SO4 acidic proton, right? You have actually you have three technically. You have either of the oxygens on the top left; those both have lone pairs; they could accept that proton. Or you have the double bond in the bottom right corner. So let's see what happens. So if we place the
About this in general, though, because I
well,
always thought it was just a catalyst.
well, you'll see. It actually is a catalyst, kind of. You'll see. I'm just gonna walk you through it real quick.
Okay.
So if we put the proton on either of the oxygens, you're gonna put a positive charge on it, and then you form like a resonance structure. You form some. You don't write this down. This isn't super important. But you form like some resonance structures, and eventually you form a strong acid that is just gonna cough up its proton to whatever's around it. So you kind of made no change if you put on either of the oxygens on the left side. So that leaves the double bond in the bottom right. If you take away that double bond and you attach a hydrogen to either of the carbons of that double bond, first off, which of those carbons would get the carbocation? Would it be the one at the bottom of the ring or the one at the bottom right of the ring?
This one right here.
Yes, because it has more charge density spread. It has less charge density. You get the idea. So you take that, right? That gives you a carbocation. And remember, carbocations are the strongest electron acceptors you know. So now you still have electron acceptors up at the top left of the molecule, right?
Yeah.
Or I'm sorry, electron donors. These oxygens both have 2 lone pairs.
Oh yes, yeah.
So it's more stable to have a positive charge on oxygen than on an electron deficient carbon. Carbocations are like the trump card. They are less stable than everything you've ever met.
Okay.
So basically, if you can get to a situation where let's just arbitrarily pick the bottom oxygen, right? So the one with the OH. So you could swing that oxygen up, and you can kind of see how when you do that, what was once coming out at you is kind of like swinging up and over the ring. I have a video mirrored right now, so I can't really like do this well. But what was once coming out at you, right? You can imagine like an arm folding down like that.
Yeah.
So that arm is like swinging over the ring and creating a smaller ring by connecting with the carbocation you just made. So first off, let's look at the structure on the right of the ore here, because I think it'll be easier to recognize what's going on. Basically, the rightmost carbon with the dash and wedge bonds, that was your original carbocation. You know that because bound to it is that oxygen you just kind of hijacked, right? And then you have the carbon with the double bond. The reason that this works okay is when you do that, you do get a positive charge on that oxygen, the one that's bridging here, not the one that's a double bond. But that can be gotten rid of with some kind of solvent molecule. And if you have a solvent molecule, right, you can pass on that acidic proton from this structure to the solvent, and in so doing, you've regenerated a strong acid. That's where the catalyst bit comes from. So does it make sense what's going on?
Kind of. I feel like I understand this one.
You understand the one on the, okay, well yeah, that's fine too.
It like kind of goes around, so that one makes
Yeah,
sense.
so in this one, right, and I think you understand it already, but just to make sure, the ring is like this, my cupped hand, the original ring, and then you have the scaffold of the oxygen structure going like that.
Mm-hmm.
So the ring is going in and out of space, and then the oxygen just kind of like wraps up. So I think you get that, right? That makes sense to you?
Yeah.
Okay, perfect. So if it helps you to think of it that way, think of it that way. But the important thing is when you do this, you're not going to end up getting like an enantiomer or diastereomer or anything like that because you only can get one product. Carbocations are planar, so you could randomly get that the ring is going up, that this new ring, right? So you take your flat ring like this. The new ring could be going up like this, or I guess it could be going down like that. But that doesn't really change anything because you're symmetric about the ring. So in this case, you don't get any stereoisomers. You only get one product. And you could play with that by saying, well, what happens if we put the ring below, or if we put the new ring with the oxygen below the original ring? Well, since you have a flat ring that's totally symmetrical all the way around, no substituents or anything like that, you end up with a neutral, or you end up with two identical bonded groups because each of them, right? These are two different groups of the carbon. They each go like that. So, take Carl.
So these two are the same thing.
Yeah, that's why I see the or. If you ever see or in a key.
Wow. Okay. Yeah, that one does make sense. Sorry, let me just turn the light on.
Yeah, I was gonna say it's getting very dark over there, but also I need to turn off my HD camera because my I just got a text from my brother saying stop hogging all the internet. So
Oh no.
yeah. The
Wow. So okay. So basically, unless like in this one, H2SO4 doesn't really do anything except react with the H2O, and then that's what reacts with the original molecule. But if you only have H2SO4 by itself, the hydrogen reacts with the original molecule.
Yeah, so the reason that that's true is that if you're you're always going to be given all of the molecules in an equation that can play a reasonable role. So if you're not given a solvent, then you can't just assume that a solvent is going to be there to play a role in the reaction that is taking the hydrogen from the H2SO4, and because it's a weaker acid, like losing out on the equilibrium with H2SO4, getting stuck with that proton, and only then being the catalyst. So yeah, if you don't get a solvent, run with it.
Okay. Sounds good. Thank you. Oh yeah. Okay, the next one. So this one. So I get why this happens, but also why couldn't the CN take the place of bromine instead of chlorine?
So, okay, this is a really, I hate this question because it doesn't test your actual comprehension of what's going on. It just tests like, here are two competing effects that we've never quantified for you. Guess which one is correct. Basically, so you know that bromine is more stable as an anion than chlorine, right? Like that's why it's a better leaving group. Or you could just say you know that it's a better leaving group.
Mm-hmm.
So because of that, you would actually expect bromine to get sheared because the bromine, you know that the bromine ends up being more stable as an anion. For all that X and Y stuff we talked about, creates a bit bigger energy difference between Cn minus and Br minus versus Cl minus and becomes more stable. The reason you don't see that is that these two little sticks at the bottom, like the bottom, so the two little methyl groups that aren't mirrored on the Cl side, even though you're going to get an attack of the nucleophile, the Cn, at a straight angle, right? Right. So it's going to come from the top right, strike that carbon, and then knock off the Br. Even though it's true, those still provide some steric hindrance, whereas the Cl is completely open and there's nothing. It's just a regular old primary. There's nothing there to get in the way of the Cn, so that happens. I really don't like that question, if it's any consolation, because it's two competing effects, and it's not testing whether you understand, it's testing whether you can memorize a specific instance, but that's why.
Okay. But the other one would be a product, just not a major product.
Yeah, exactly. That's exactly it. Um, the line between major and minor is kind of ridiculous. I usually err on the side of professing one major product, but the whole concept of major versus minor products doesn't suggest any comprehension. It's just kind of an artificial test, the idea. So A, don't feel bad if you don't like get it, because I still don't get it. I still don't know what they want, and I teach this class. But B, I would always err on the side of if you know that one is going to be present more than the other, like in this case, we established, we didn't prove because we have no experimental data, but we established that you'd see more of the Cl being knocked off and the Br being knocked off. I would include just the one.
Okay. Sounds good. And why wouldn't, because it's a, oh wait, no, it's a primary, not a,
Mhm.
oh, okay. And that's why I wouldn't get usage.
So the
Okay.
energy difference between the product you actually see and a hypothetical alkene one outclasses the ease of rate having the that plus remember CN is not a strong base. It has a its conjugate acid has a pK of like 7.2 or something like that. So basically you would never I hate memorizing, but for your test you wouldn't see CN with E2. You probably wouldn't see that. I mean, maybe if you have some super sterically hindered alkyl halide on the other side, but yeah, that makes sense.
Yes.
All right.
Thank you. Oh yeah, okay, so the one after that, so I also got these two. First of all, I don't understand why this is minor, but also why wouldn't you get a double bond right here? I don't know if you can see my cursor or
So you're
not.
saying from the top right carbon to the top carbon, the top middle
Yeah,
carbon. Okay.
yeah.
So that would be identical to the left product because you could just rotate that you could rotate that molecule about the axis that's formed by the methyl group and the carbon it's bound to, and then that bottom left carbon. You can just rotate that. Everything's planar because there's no bond.
Oh, I see. Okay,
So
yeah.
you would get that. You would get that, but it's a minor product. If well, you would get that, but it's identical to a product you already have. So, Noel, hello. I saw you joined. We're recording this, and you could sue me if I didn't tell you that. Do you have a problem? No? All right. We're just going through some old tutorial problems right now, so feel free to chime in if you have anything. But for now, Karen's has a whole bunch of questions, so I'm sure it'll be helpful for everyone.
Yeah, Noel, if you have any questions too, just jump in.
You're muted, by the way, Noel, and I don't think you know that.
I'm all set, here to listen.
You're here to listen? Okay. I love it.
Okay. So then why would this one be minor and not, or like why is this one less favorable than this one?
It's an energetics issue. So the one on the right is less stable. The product on the right is less stable than the product on the left because you have fewer alkyl substituents on the double bond.
Oh yeah, double bonds have that rule too. Yes.
So again, I hate the idea of calling it a minor product because you absolutely would get it, but you would get less of it because it's less stable, right? So the reaction has two pathways it can go from its intermediate. Because this is SN1. I hope you agree with, or I'm sorry, E1. I hope you agree with me on that. But it's E1, so you have the carbocation, and from there you can go to either of these products like freely, and you're just way more likely to end up at the one that's more stable. There's also two separate hydrogens that you can nick, right? You can nick a hydrogen from the bottom right carbon of the ring or from the top middle carbon of the ring, and we said that those would be identical products. Whereas you can only nick one set of hydrogens for the top. Does that? I'm sorry. Let me rephrase that. You can nick 4 in total because there's 2 on the top middle and 2 on the bottom right. But there's only 3 on this side methyl that you can pick that would give you the E2 you need to get the right side. So in addition to the stability difference, there's 4 versus 3 candidates to get like swiped in a reaction. So does that make sense?
Yes, that makes a lot of sense.
Mm-hmm.
And yours, okay, so you said this is E1.
Mm-hmm.
So H2SO4, again, I was confused because I didn't realize that like it can just kind of do things by itself.
Mm-hmm.
But I've seen a couple of instances where it's like H2SO4 and little triangle thing.
Yeah.
Would you mind showing the mechanism for that?
Yeah, I can do that. I'm gonna try something because I'm too lazy to go back to my board. So A, don't judge me. But B,
Do you want me to
let me.
stop?
So if you could stop that. So I'm
Yeah.
gonna pull up something that lets me, and I'm gonna get my mouse, and I'm gonna draw for you on my computer. So basically, the reason that you get. Actually, hold on. Let me wait till I actually get this out. Okay. So first off, I realize I'm not screen sharing, which means, okay. All right. So what is this? I don't know what that is. I hope there was context for it.
That was bio.
Is that bio?
That
Oh my
sounds
God.
like bio.
Yeah. Well, this, the X's, yeah, probably. So let's see. So you ended up, the original product was this, right? And you're gonna have to put up with some terrible drawing. So I hope you're ready for that. I only get paid $9 an hour. I'm not breaking out the tablet for this one. So you have this plus H2SO4. The little triangle thing just means heat. So heat is just a way to help overcome reaction barriers. Right, you're giving things more thermal energy, so they're more likely to bump over a reaction barrier. Same reason cellular respiration becomes more favorable at higher temperatures. So basically, right, H2SO4 is a super strong acid. It's the strongest one you know. So second strongest, third strongest one you know. So it's going to protonate anything that with a lone pair that can accept it. In this case, you have one thing with lone pairs, and it's this oxygen, right? So the first step is that you take that originally from sulfuric acid hydrogen, which I've drawn abysmally, and you get this thing, right? This positively charged. Okay, there's a bump in my table. That's why it's this bad. But does that make sense generally? Like what's going on here? The alcohol oxygen, the OH oxygen, picked up a proton. But now we have a positive charge on this. Oxygen with a positive charge doesn't play nice. if we could somehow just get rid of one of the bonds that it has and give the electrons back to oxygen, we would be in a situation where we have just a neutral oxygen with 2 bonds. So we could get rid of the bond to one of the hydrogens in an acid-base reaction. That puts us right back where we started. Or we could get rid of this bond. So I'm going to try to avoid the gap in the table here. So if we get rid of that bond, and what I'm doing here is I'm moving the electrons from that bond to the oxygen, we end up with our original ring here, right? Now this carbon right here only has 3 bonds, so it's plus charged. And we also have an H2O, which was originally our OH. The second hydrogen comes from the sulfuric acid. We have this H2O lying around, and that H2O is way more stable than that positively charged oxygen. So, at this stage, this is where we get at that SN2E2 divergence point. What's going to make the difference here, usually with a strong acid, if you were using HBr, right, you end up with something that can be like an acceptable nucleophile in Br minus. Because once you use HBr to protonate something, you end up with a Br minus on the end. So in this case, though, you have, and I'm not going to try to draw it. It's going to take way too long. But you also have, this is so ratchet. Okay. OSO3H. I don't even think you can see that. I'm going to try to. So you formed in the reaction, right? This is the analog to Br minus if we use hydrobromic acid, right? You agree with that? So this is, in SN1, we can play with terrible nucleophiles, but this is a really terrible nucleophile because A, it's super big, right? You have the S in the center with the double bonds to an O up top, double bond to the O on the bottom, single bond to an O minus, single bond to an OH. It's super big. That's problem 1. Problem 2 is that it's way more stable than your average anion because of all the resonance going around. So it's actually going to be unfavorable for this OSO3H anion to just collapse back and form a bond here, so that if you follow my cursor, you end up with the O here, the central S here, double bonds to an O here, double bonds to an O here, and then OH. That sucks because you're using, some people call this a mineral acid because you have the sulfur in there, but because you're using an acid that gives you a horrific nucleophile in exchange. The other thing we can do, the other option we have, is to use this as a base. Just like with SN2 versus E2, we can alleviate using this as a base by, we can alleviate steric strain by using this as a base and having it attack the periphery of the molecule, rather than by having it go right in the center of this 3-carbon complex. Therefore, in this case, you're going to see this with sulfuric acid, you're going to see this with phosphoric acid, which is like H3PO4. Because of the way they teach this, and I'm talking through gritted teeth right now, you have to memorize that.
Okay.
So,
And do you mean E1, not E2?
if I've said E2 with this reaction, I mean E1. I need to work on that.
Okay.
Yeah.
Okay. So those two lead to E1, not instead of SN1. Because they didn't really talk to us, because they told us you won't be able to tell whether E1 or SN1 is more favorable than the other.
Which is a freaking cop-out, because you can if you think about it, but you do need experimental data to like base that from. Like the only reason, we have no reason to say here, oh, well, the steric effect is definitely going to be bigger than the effect favoring SN1. We can't say that. The effect favoring SN1, remember, is the difference in stability between something with a double bond and something with no double bonds. So, yeah, if you're memorize, if you're dealing with H2SO4 or H3PO4, you're going to get E1 instead of SN1. In almost every other case, SN1 is your major product. Do you include E1? Usually not. Consult your answer keys for that.
Okay. That helps a lot. Awesome. Okay.
Okay, I can stop sharing that mess. I guess you're gonna have to start screen sharing now again, aren't you?
Yes, remind me how much time we have.
33 minutes.
Oh, perfect. Okay.
Mhm.
I'm just gonna go back inside real quick, but because it's cold. But I'll tell you my next question before I do that.
Okay.
So if that one made sense. Okay, so this is like a similar question to the one I had before.
Mhm.
But for this one, why? So I know this one has to stay the same, but why couldn't these two both be facing out or both be facing back?
You are currently buffering for screen share. Oh, there we go. Okay. You are
Or
pointing to
because
D.
the bromine always comes from the other side?
Are you pointing to D?
Yes.
Okay, so you're saying why can't the BRs be syn?
Yeah, and is it because like I'm thinking now because the second bromine always has to come from the other side.
Yep.
In comparison. Okay.
So yeah, you can go inside now. Like you have my permission, I guess. Not that you needed that. But yeah, that's exactly it. The BR2 edition is anti because when you have the bromonium bridge that's an intermediate, you can have the BR come in from the bottom, which because of budget cuts, I'll have to use my nose for, right? You got the BR coming from the bottom, right? But to get through the top, you have to cut through that bridge. Can't do that.
That makes sense. All right, my next question was about part E.
Okay.
I saw the HV thing a couple times, and I don't know what that means. What was supposed to do with it?
Okay, so that is chemists trying to be cool by using quantum mechanics symbols for light. That's light. H is Planck's constant. That V is technically not a V, it's a Greek letter, but it means frequency. So basically what that means is that you have a light of a certain wavelength hitting. If you ever see H nu or HV, that's light. If you remember all the way back to Gen Chem, your equation like E equals HV all the way back, like when you're talking about promoting things up energy levels, that's where that comes from. Or you can just memorize the triangle is heat, the HV thing is light.
Okay. Is that supposed to like matter?
It does. It does. Let me know when you're able to listen.
Yes, I am.
Okay. So it matters. BR2 edition has two modalities. There's one in which you have a double bond, right? You have a double bond, and you're adding to that double bond. And for that, that's just a standard addition reaction. You're not going to be using any. You're not going to be using any. How can I phrase this? You're not going to be using any radical initiators or free radicals for that. That's just a totally normal and great and chill addition reaction. If you don't have a double bond, and in this example, you have benzene double bonds, but remember, for reasons that you don't know yet because of the way that the course is taught, ITIC, the benzene bonds are almost invulnerable when it comes to the addition reactions you're learning right now. So in this case, you have BR2, but because benzene bonds are so sick, you don't have any double bonds that it can add to. So that means that you have to go to the second modality of BR2 reactions with carbon groups, and that is that free radical halogenation of alkanes reaction. So this is from chapter 4. This is unfair, but basically, or it might be from chapter 5, but basically what's happening here is you are forming a BR radical. The reason you know that you can do that is because light energy has been provided in the form of H nu to break the really weak bromine-bromine bond. So remember, bromine is an electronegative and large element. So it being electronegative means that when it's bound to itself, right, you're going to get little electron density in the middle, and then more electron density as you get closer to the ends of the bond. So that makes it a weaker bond because both bromines are pretty close to being bromides. Like they're just a little bit of strength away from pulling those electrons all the way in. And they're also big, which means that the bond is spanning a long distance, but it's still 2 electrons, so it's weaker that way. I'm telling you all this to tell you that Br2 bonds are weak, and just a little bit of light can break them. The same thing is true for hydrogen peroxide. OO bonds are really weak because of how electronegative oxygen is. And that's why hydrogen peroxide is always shipped in those dark brown containers. Because if it were shipped in something that let more light energy through, it would cause free radical reactions that would degrade all of the hydrogen peroxide in the bottle. That's just like a fun fact. That's not something you need to know. But because of that, the weakness of that bond, you're eligible to get a free radical reaction. And because of that, you can do a funky little mechanism where you form two Br radicals by just splitting that Br bond, right? So you take that bond, each of my fingers represents an electron of the bond, and the fist behind them is the bromine ion. You take that bond, you split it, one of the electrons goes to the left, one of the electrons goes to the right. So when you have it like this, each of the fists is touching 8 electrons. Now they each have 7. They are 2 bromine radicals. That is your initiation step. Your propagation step, you take that bromine radical and you, what chemists call abstract that hydrogen from that top right carbon. So basically, you're going to be reconstituting an HBr from a Br radical and slapping that radical on the CH3, CH3, and benzene carbon, if that makes sense. So after that, right, the easiest thing to do, now you have, I'm going to represent the benzene ring by my fist and the 2 CH3s by my fingers. You now have a radical there, so there's a free electron here. And you have all of these Br2 atoms, or I'm sorry, molecules nearby. Well, that electron is, remember, free radicals are infectious. That electron can swipe one of the Brs from here, take one of the electrons from the Br-Br bond, and form a 2-electron bond with one of the Brs from the Br2. The other Br is going to end up with 7 electrons. So then you get a cycling radical reaction. That is why you get this reaction. If you didn't have light or heat or peroxides or any radical initiators, you would expect that because there's no reactive double bonds here, there'd be no reaction.
Yeah.
Light and heat for your purposes are indistinguishable. So
Wait, so then, but this one was not a,
so you're saying why was D a standard addition mechanism as opposed to a radical? The answer to that
Yeah,
question is
because this is a good base, or I
hold on.
mean acid, sorry.
So hold on. I'm sorry. Which one are you on? You're on B?
Yeah, so I'm saying for for E, sorry, for E, that one had radicals,
Yes.
but B did not, even though it had heat, because H2SO4 is a strong acid.
So remember that light is only enough to break the Br-Br bonds because they're so frail and weak. For the 2 things I talked about, they're huge, so it's 2 electrons spanning a large distance, and they're electronegative, so there's little electron density in the middle and a lot more towards the ends of the bonds. That makes a Br-Br bond really weak, and all you have to do is excite one of its electrons with light, and you break the bond. H2SO4 has much stronger bonds. The SO bonds they're all pretty resilient. OH bonds are strong, even if it's a strong acid. You're not going to get, excuse me, you just don't really get like an H2SO4 radical, if that makes sense. For your purposes, because you have a test and because that's the way this class is taught, I'll tell you that you usually only see radicals with bromine and then sometimes chlorine, and then and those polymerization reactions you talked about earlier. Those are the only times you would see radicals. H2SO4 doesn't radicalize. But the reason for that is that you need a really weak bond to form radicals. Peroxides have that. That's why they're radical initiators. They actually beat bromine to the punch in terms of breaking their bond and initiating a radical mechanism. Or you need lighter heat. Conceivably, if you had enough heat and enough light energy, you could get a radical reaction for B, but you would never see that in this class. So, does that answer your question?
Yes.
All right.
Wow, that's a lot. Oh, okay. But it does. That makes sense why that happened. And so wait, so the H just gets taken up by a bromine to make HBr.
Yep. And then that bromine was originally radical. You have to have an even number of electrons on both sides of the equation. So the carbon to which the H was bound picks up the radical.
Wow. Okay. Okay, this one I just had a question. I don't think it matters whether I put the carbocation here or here, but just to make sure it doesn't matter. If I had, while I was working it, I put the carbocation here on the right.
So what's the difference between putting the carbocation on the left and putting the carbocation on the right? There is none, because you could draw an axis of symmetry. So draw a line from like the D in intermediates in the direction. So start from there, draw it through the oxygen, and then right through the center of the ring you drew. And you'll see that if you take that axis I just formed, right? So from the E or the D in intermediates through that oxygen, through the middle of the ring, you get a rotation point. You could rotate the structure you drew around that line and end up with the exact same thing, but the carbocation is on the right side instead of the top. So it would not matter.
Okay. Thank you. Oh yeah, okay. So for part C of this problem, so why did we assume that, so the only reason, like whenever we do these problems, the only reason we know that a methide or hydride shift is going to happen is basically because they gave us the product. And so for part C, when they ask us to form one of the products, why do we assume that that shift happened? Wait, actually. Well, I guess my question is like, for part C, do we also assume that whatever happened here kind of happened here, except for the E2 versus SN2?
So
Oh, sorry, the
E1 versus S1, yeah. You caught yourself. So first off, E1 and SN1 diverge at the point of a carbocation. They don't diverge earlier. So that means that the exact same carbocation that you use for SN1 would be the same one that you use for E1.
Okay.
Because of that, if you have a methide shift that makes it the SN1 carbocation tertiary, because E1 reacts from the same base, like the same base, not bases in like hydroxide, but bases in like starting point. Because they both react from the same foundation, if the foundation had a methide shift in SN1, it has to an E1.
Okay, that makes sense. Thank you. Okay, that's all for this one. But of course I have another one.
Oh, I love this. I'm actually like helping instead of just shouting at my camera. This is great.
Okay. Yeah, this is okay. And thank you so much for your email, because otherwise I would have had to wait like until Tuesday for them to release the key.
Hmm. That's actually evil. Why are they like this all the time? I don't. Why?
Okay, so now that I kind of understand nucleophiles more, I'm gonna
Mhm.
try to figure out what I didn't understand earlier.
So do you want me to just like say nothing until you call for me for aid, basically? Because I feel like that's a good way to do this.
Yes, let me turn on my video real quick because that might be slowing things down. There we go.
Okay. Yeah, it looks like that helped. I'm finally getting the key.
Can you see it?
I can see number one with the CN versus the carboxylate. Yep. I think, yep, I can see it.
Okay. Okay, so I got that it was SN2.
Hmm.
Oh, and that makes sense. B would be, even though the oxygen is more electronegative, the CN, because it's smaller, is better for CN2.
So
Okay.
yes, and that's one factor. The other factor is that that oxygen is not as unstable as your average oxygen because that oxygen has resonance stabilization. So it effectively has half a negative charge instead of a full negative charge. So luckily they gave you a good problem. Both the steric and the resonance effects point to the same conclusion. So you're all set.
Oh, great. And if it was just one of them, would the CN still triumph over that?
So if you cut off if you replace the double bond to an O with two hydrogens, you mean? In that case, you would probably see the ethoxide win. But again, like that one, yeah, you would probably see the ethoxide win. But you also have more sterics, so I couldn't tell you for sure. You wouldn't see a problem like that, I don't think.
Okay. Sounds good. Okay, and then next question was on number 2. No, not on number 2. On part 3. So let's see. Oh, wait. We could talk about this. Yeah, because of steric hindrance, it's going to be E1.
So, I'm sorry, go ahead.
Oh, no, you're good.
Yeah, you're exactly right. So, question for you, why wouldn't it be SN1?
Well, because of steric hindrance.
Because of
If the
steric hindrance, yeah.
H2SO4 is
Yeah,
too big to get in there to get to the carbon.
yeah. It can't form a stable bond. It can't get in there to form a stable bond. And even once it does, its bond is going to be really weak. So, yeah, exactly that. Yeah, or you could say you have a mineral acid, it has a sulfur or a phosphorus, therefore it's E1 over SN1. But yeah,
Okay, that would make sense. And then A is faster than B because, hold on. Because, well, I mean, isn't A more stable because of all the double bonds? But I'm not sure.
so, okay, A is faster. Something I didn't talk about up there, because I didn't really talk about rates that much, because I don't know why they introduced them here. But um, the rate determining step of SN1 and E1 is carbocation formation. The reason for that is that, right, here's your energy, right? The yellow eraser cap. huge spike up to get to the carbocation. So you're starting off like here. Huge spike up to get to the carbocation. That's a huge energy hill to climb. But once you get there, you're going to almost immediately careen downward to your products. The reason that you are more stable, or you're faster in A than B, B is actually not less stable than A for reasons that basically boil down to, again, double bonds are less stable than single bonds. Well, yeah, double bonds are less stable than single bonds. So even though there's that like weird benzene stuff going on there, but it's way easier to form a carbocation when you can resonance shift that positive charge all around the benzene ring than it is when you can't separate that charge with the cyclohexane ring.
Wait, doesn't the carbocation happen on this carbon right here?
Yep, it's the one right where your cursor is.
So why does this matter if this is like happening here and not here?
So basically, so you have a positive charge in place of the bond of the OH, right? Just take the bond between the top middle and top right carbons of your ring, and just kind of like, so it's like this now. Flip it over like this. So it exits the ring, and it's going from the top right of the carbon to that carbocation you just formed. Now you move the positive charge from that chain carbon to the top middle of the ring. Does that make sense? If not, I, draw it out.
Yes, that would be good.
Okay. I'm gonna have to kick you off of screen sharing, so just give me 1 second. Okay, we're gonna go back to Sketchpad. All right. Hopefully, that's not what you want, Joey. All right. So you have this, right? I'm just going to abbreviate it by putting the positive charge here instead of drawing out the whole thing, right? So we had this bond, and this bond. Okay, you agree with me so far, right? What is stopping me from taking, so this bond, the bond is just a collection of 2 electrons, right? What is stopping me from getting rid of that bond and replacing it by, like, just kind of moving it over here? What's stopping me from doing that? Because if we do that,
benzene ring, so you can't really.
and this is why I wish they taught you aromaticity before they actually taught you all of this. Benzene rings are stable, like in the extreme, but the carbocations are unstable in the extreme.
Okay.
So again, if you understood aromaticity because they taught it properly to you, then this would make intuitive sense. But they didn't. So basically, I need you to take on faith that dispersing the positive charge of a carbocation, because then you could also do this, right? And then you end up with this structure where you now move the positive charge down here. All right, great. And you have those bonds, and then you can move this bond like that and put the positive charge here. Basically, I need you to just accept on faith as like a postulate that that is more stable than preserving the benzene ring. You might see that the positive charge remains on this carbon here most of the time, because every time that you slide electron density over here, you are lessening you're getting rid of that aromaticity, but you can still spread the charge over here. And remember, lowering charge density is more important than lowering charge. So because of that, you have stabilized the molecule. Because of that, you have created an more easily formed carbocation. Because it's more easily formed, there's a lesser energetic hike to get there. It has less activation energy. Because of that, it's formed faster. That's why A is faster than B.
Wow. So basically, resonance.
Basically, resonance.
That makes sense. Okay.
You have 9 minutes, by the way, just so you know.
Yes. Thank you. Okay, so I think, yeah, I understand. And then, oh wait, on this one, why wouldn't an E2, why wouldn't an E2 reaction happen for the last part here?
So E2, right? In an E2 reaction, first off, your instincts are in the right place. I would expect an E2. N3 is not a super strong base, but there's really no way you can know that. But basically, for E2 to happen, you need to remove a hydrogen from a neighboring carbon.
Oh, right.
And so the neighboring carbons to this carbon, well, there's a Cl, that doesn't count. There's the tip of a benzene ring, which has a single bond down to the carbon we're talking about, a single bond down to another carbon of the ring, and a double bond to the other carbon of the ring. And because of that, that's 4 bonds. You can't have a 5th bond for a hydrogen. So because of that, there's just no way to have E2 because you don't have what's known as an alpha hydrogen, a hydrogen on the carbon next to the carbon with the leaving group.
That makes sense.
Mm-hmm.
Okay, thank you. The next question was, okay, so on number 8, well, can you see that?
I'd appreciate if you scroll up a little bit so I like as far as you could so that I could still see what's going on for part 2. Okay, so ER5 heptene 2-ol reacts with bromine to give the brominated ether product. You didn't hear that voice crack. Get the brominated ether product shown. Okay. Do you understand part 1A, or were you asking about part 1 or part 2?
I was asking about, wait a minute. Sorry, I forgot that the numbering on ours was different from last year's.
Of course it was.
The okay. Yeah, I'm asking on one before that.
Oh, you're asking about 7, the mechanism, or are you asking about?
No, I think I'm asking about, yeah, I'm asking about this one right here.
You're asking about 3 on with the OH with CN.
Yes.
Okay.
So basically, I get the CN part, that makes sense. I don't understand why we had to add this up here.
Okay. First off, can you tell me what SOCL2, PH3, PBr2, TSCL do?
No.
Okay. So basically, there are 2 ways. The end goal here, our mission, is to somehow change that oxygen, change that alcohol group, do something to make it better at leaving the molecule, right? Because it needs to get kicked off so that the CN can come in. You agree with that?
Yes.
What these reagents do, so there's 2 ways to do that. The first is to nuke it with strong acid. That gives you that OH2 plus group, which can then just kind of fall off on its own. There's one small problem with that here. That only really works through a carbocation mechanism. And here you would be forming a primary carbocation that is in no way resonance stabilized. That is going to get you points off. So you can't really, I mean, you actually kind of could. I hate the way they teach this, but for your intents and purposes, you can't just nuke this with strong acid. So if that weighs out, we need some way to make an OH group a good leaving group that does not involve a strong acid or a carbocation, right?
Mm-hmm.
So Socyl 2, what that does, sulfonyl chloride, sulfonyl dichloride, what that does, through a mechanism that you never learned, it replaces the OH with the Cl.
Oh.
Basically, the Socyl molecule is really unstable. So it's like very, I don't like the word willing, but it tends to give off, it's willing to slap that chlorine on something else. And oxygen happens to be, so basically you're just going to replace the CO bond with a CCl bond. And if you do that, congratulations, you now have a good leaving group and you can use NaCl. PH3PBr2. Again, I would go through the mechanism, but it's 9:58 and I want to give you time for one more question. This isn't that important. That replaces the OH with a Br. So you're replacing the COH bond with the CBr bond. Tosyl chloride replaces the OH with that OTS thing. I could show you what that is. I don't think it's I wish I could, but I want to give you time for one more question. OTS group. So in this case, you're not actually changing the CO bond. You're changing the OH bond, and you're exchanging the H for what's called a tosylate. And basically, OTS is a really good leaving group. It's kind of like slapping a Cl or Br on there. And you can go ahead and use NaCl.
Wow. That makes a lot of sense. Thank you.
Yeah.
Okay, so similar question for the next one. So ours was actually, the one that we had, it was I'm guessing it would have been H2O because there was no, it was just a hexane. Or pentane, whatever that is. But why do you need the magnesium or lithium first?
So have you learned organometallic Grignard organolithium reagents? Do those words mean anything to you?
No, but it was on our practice exam.
It was on your practice exam, but did you ever learn about them in lecture?
No.
So, okay, basically what you're doing here is you're creating what the Mg and Li do is they basically form a really unstable carbon-metal bond when with the Br. And when you do that, because carbon is more electronegative than almost every metal, the carbon effectively acts like an anion, and it's going to reach out and grab anything it can find. In this case, H2O or D2O is just an acid-base reaction. Excuse me. I don't think you need to know that, though, if you have never heard of Grignard reagent.
Okay.
So, yeah, it shouldn't be on your practice test, but I'm not surprised.
Okay. Sounds good.
Okay.
Thank you so much, Joey.
Yes. If you want one more question, I can do one more.
Are you sure?
Yeah, because then I just stay clocked in for longer.
Okay.
Yeah.
I'll help you do that. Okay.
Thank
So
you.
over here, why is the alkene trans and not cis? Because it looks like it was cis over here.
So,
Oh,
wait,
wait, no. Because the bromine has to come from the other side, so for that to happen.
Yep, you got it. So you'd have to rotate around the bond in order to get,
Uh-huh.
because this is not the most stable conformation of this dibromide compound. You have to manipulate it by rotating what would have otherwise been an upward moving chain and get that part moving down. And in so doing, you take the BR group that was going into the page, and when you rotate it, it has to come out. You got it.
So why do they have to put it in this conformation though? Like, why couldn't they put it this way and have like one bromine coming out and one coming? Or I guess they were just trying to test us on that. Okay.
They were trying to trick you. That's all they were doing.
fun
I don't
stuff.
think the goal of chemistry should be tricking people, but here we are.
Okay.
So, all right.
Alright.
Well,
Thank you.
I'm gonna head out. I'll probably post something in the group chat like tomorrow about doing a meeting with our little bio group in case anyone wants it. But if I don't see you till then, you'll do fine the test, I'm sure.
Thank you, Joey. And good luck with your stuff too.
Oh, thanks. But it's not a problem. We might end we might end up being mandatory pass fail anyway, so we'll see.
Honestly, I'm hoping for it, but it's fine.
Yeah, I think I have perfect A's this semester, and there's like no chance of changing that. I'm still a supporter of mandatory pass fail because it's like med schools might not accept or grad schools might not accept AP, and then your fail safe
no.
for people
You
who
know
are
that.
legitimately impacted by online learning is gone. Like you could claim the P, but then it's just weighing you down as much as an F would. And like there's no safety net then for people who are legitimately in trouble. And I don't like that. But
That is true. Yeah.
all right. You've probably had enough of me ranting, so I'm going to end the meeting. But I'm glad this could help.
Thank you. And also, don't forget to send it to Bree.
Oh, I'll you'll probably need to text me tomorrow, but I'll do my best.
Okay.
All right,
Alright.
Karen.
Have a
See
good
ya.
night.